Okay. Okay, hello everyone. Thanks for coming here. My name is Mauricio Agudelo. I am the CEO and one of the co-founder of Bialtec. And today I'm going to present some of the works that we are doing. This is a research focused on high performance cattle, how to improve or enhancing the rumen function and improve the milk production. So today we are going to talk about probiotics, but not any probiotics. Let's explain a little bit more. But first, let's talk about Wisconsin state and the production of milk. Wisconsin is the second largest milk producer in U.S. They produce about 30,000 billion pounds of milk per year, and some farms can get 31 kilograms per cow per day. So this is very important, very high productivity market. So when you have this kind of market, you face very important problems. One is you are producing at top level, so you need to have healthier animals, but also you need to look at how to be more efficient. And when we talk about efficiency, we need to understand if we are able to increase the energy that we can extract from fibers, for example, or from the TMR, the diets. And finally, sustainable. Lower emissions, that means lower manure and lower greenhouse gases. In principle, if we understand the cow as a system, as a bioreactor, when we are feeding some nutrients and we are improving the absorption of those nutrients, then we can infer that the excretion or the output will be less. And that's the point. That's the point. How we can enhance the efficiency of this cow to absorb or maximize the absorption of nutrients and avoid or reduce the losses in the excretion. Let's talk about the approach that we have for this problem. At Bialtec is a scale-up company. We are a Dutch company. We have operation in Europe, also in South America, where I am original from, Brazil, Peru, and Colombia. Our approach is to produce a platform to design and produce microorganisms, like bacteria, by microencapsulated. Why this is so important? As maybe you might know, probiotic or live bacteria is very sensitive to thermal, oxygen, light. They can just grow, for example, inside in the rumen in anaerobic condition. So then when you take out, these cells can die easily. And now in this world where different probiotic companies appears everywhere and everyone are offering a value that this is the better or the best probiotic compared with others probiotics in the market, our approach is to protect them, protect all the probiotics that are available and even the new probiotics or the next generation of probiotics that can be developed. And this is key because, as I mentioned before, if we want to isolate and to grow a microorganism from the rumen, for example, a Ruminococcus, a Prevotella, or a new strain of probiotics, it's important that these cells can be protected against light, against storage condition. Even if you want to put into a pellet, so you need to protect against thermal processes. And if the bacteria is anaerobic, so it's more sensitive. Then the idea is to cover the cell with a shell, and that shell is to protect them. But the shell must be special because the shell needs to release where we want. For example, in rumen or downstream in the gastrointestinal tract, in the colon, or before in the I forgot the word. Then I will back with that word. Sorry. But the idea is that we need to protect this bacteria, and there are many bacteria now in the market that we need to combine with some antibiotics, for example, or combine with mineral salt, and they can get temperature, but water, and water can destroy the cells. So in behalf of my team, this is the scientific team that we have when we have PhD, Magister in Science, that have been working in this in different places in the world. I have the responsibility to try to tell you the science that we are developing and how far we have been with this. So first, I want to back in these images. What you can see inside the picture is a set of lactobacillus. Lactobacillus are strains like we can find in yogurt, for example. And as you find in yogurt, if you leave the yogurt storage temperature, room temperature, after 2 hours or 4 hours, they're going to waste, spoiler. So when you dry the microorganism that the yogurt contains, so you're going to have a powder, and the people that produce even cheese or yogurt, they know that they need to store the powder, the probiotics in the refrigerator. Otherwise, it's going to lose activity. But then is the technology that we develop, is the coat, the shell that cover a bunch or a cluster of lactobacillus. This coating process is made with a modified fat. So as you know, fat is hydrophobic. So water cannot get into that. Lye is more difficult to get into that. So with this shell, you can use lactobacillus or other bacteria like bifidobacterium, yeast, and put in a pellet, a storage temperature, even high temperature, and is going to resist. Because this fat can absorb part of the energy of the thermal process and can isolate the lactobacillus from the other condition. But the important thing is this fat can be hydrolyzed and can be breaking down into the rumen or into the small intestine. I found the word now. So it depends because the pH and temperature, the internal in the gastrointestinal tract, depending on the animal, will allow to release this bunch of different microorganisms. So the technology here is what will support the use of new strain of probiotics for the animal industry and even for human industry. This is not it's a eukaryota, it's a yeast that is bigger than the prokaryota, than the lactobacilli. This is a bunch of cells of yeast in this picture. And this technology showed also the cover. You can see around the bunch of cells the cover of the fat that protect them. And this is when we simulate or when we put inside the animal that break down and allow that the live bacteria can get out and do the function that we are looking for. What happens if you don't encapsulate a microorganism? In this picture, we can see that the cells or the bunch of cells is damaged. And this damage is for all the conditions, like temperature, like storage, and is normal. So then we need to ask ourselves when we are buying probiotics for different suppliers, what is the survival rate of these probiotics? What is the technology to protect them? In the market, you can find, for example, bacillus that they protect themselves, but many of the new strains and the new probiotics, they need a protection, a proper protection, and they need to be consistent with the animal species we need to target. In this case, for example, rumen and a small intestine. This is other bunch of microorganisms they call bifidobacteriums, and also we can find the capsule. So this is a patent that allows to protect sensitive bacteria, and I just want to make this pause and to explain a little bit what microencapsulation technology is, because that supports what we can do with our probiotics. Now, having into account the technology of microencapsulation and how important is this technology to support the function of the probiotics, so let's back with the research that I want to present. And in this research, I just want to leave clear that we are going to focus in digestibility. Probiotics can be used for different approaches to improve health, to control pathogenic bacteria, reduce inflammatory processes, but in this case, they also can be used to improve the digestibility of dry matter and fibers. And why? Because probiotics or live bacteria can produce enzymes, extracellular enzymes. These enzymes, if they are cellulolytic enzymes, so they can break down the fibers. If you can improve the size of the fibers, reduce it, the fibers are made also from sugars, for cellulose, for example. But the link between these sugars is so difficult, so if we can break it down or put in small pieces so the animal can extract energy from there. And that is our approach, to have the perfect or the most perfect consortium or microorganism that in the condition of the rumen can produce enzymes or help the other community to produce extracellular enzymes that help to improve the digestibility of the dry matter. So that means that we will be able to extract more energy for our diets, and I am talking specifically for TMRs. If we can improve that, so we will be able to produce more milk. And there are some studies like this one that say if you can improve 1% of digestibility in neutral detergent fibers, so you will be able to improve up to 0.25 kilograms per meal per day. But let's back, why is difficult to improve 1% of digestibility? 1% is almost nothing. But this is the thing. Here in US and in some countries in Europe, as I mentioned, TMRs are the more digestible diets possible for animals. So they are in the top. Other things happen in South America, where we work. There we are able to improve the digestibility of fibers up to 10% even, sometimes, 10%. It's a huge gap. But here, 1% is so difficult because the TMRs are full of starches, they have the fiber, but the time retention in the rumen is so small, so you need that the microorganisms work faster. And if you are able to increase this 1%, so you move the boundary and you can produce more milk. So modern TMRs are really high digestibles. They have digestibility in the neutral detergent fiber more than 50%. The high producing cows consume 24 kilograms of dry matter per day. It's a lot of dry matter, so the time retention sometimes is not well enough. If you have a grass cow that are just eating grass, they can have 24, sometimes 30 hours of retention in rumen. In 30 hours, you can destroy it or breaking down fiber and everything, more efficiency. But if you have just 16 hours, like happened here, or sometimes less, sometimes 8 hours, some authors say 8 hours, so the time is limiting to improve the efficiency in your farm. Lignin cross-link set also limit the extraction of this energy. So gain 1% will bring more efficiency. And if you look at the historical data of Wisconsin and upstate New York, the improvement every year in production is about 1% every year. So the technology is moving like 1% every year to improve the production. And it's happened for the last 10 years. So still, every time is more difficult, but still there is a gap or a possibility to keep pushing the boundaries and extract more energy from the TMR diets. So the first approach, when you want to improve the digestibility of diets and fiber, you can go, according with our methodology and the science, is to go to in vitro systems. What in vitro systems are? They are simulators that mimic the gastrointestinal tract of cows, of ruminants. So they are try to be a model in the lab that we can control, and we can see in this in vitro model how's going to happen if we nourish this cow with a specific diet or with other diet or with one probiotic or with other probiotics. So we have our own simulators, our own gastrointestinal simulators. But first, when you have this equipment in the lab, you need to validate that this equipment has a good correlation with what happened with a cow. So the first step is to have this strong correlation between the simulator you have in the lab and what happened with the cow. So we perform some trials. This is one of the papers we have when we evaluate the functional and microbiological effects of microencapsulated probiotic consortium. We did in parallel in cows, but also in simulators. And when we did this, so we are able to address much better the functionality and infer if then we can make changes in our simulator and expect to have the same benefits or be able to infer benefits from the simulator into the cows and translate into the cows. So that's the first part. We need a simulator that is validated. In this validation or in this paper, we can see that we were able to have a correlation up to close to 1% in pathways in enzyme composition. In microbial composition is not as good as we expect, just 0.67. So that means an important conclusion. You can have different microbial communities in the rumen of the cows. You can find different microorganisms. But then if you look at in the pathways and the enzyme composition, that means the functionality of the microbial ruminal community, and you find this correlation, that means that different microbial community can produce the same effects in pathways and enzyme production. It's like it's like if we have people that here can work in software, and then in Europe, other people also are working in software. They have different names, so it's a different community, but they have the same functionality that is produced as software. In this case, it's the same. We have different microorganisms that live into the rumen, but even with these differences, they can produce similar pathways and similar enzymes. And if we can look at the enzymes, so we will be able to see that, for example, when we use our probiotics, we increase the production of cellulase, silanase, some pullulanase, and all of these enzymes helps to break down fibers. So if you are able to break down fibers, again, we will be able to produce more milk because we will be able to extract more energy from the same TMR diet. As I mentioned, we have been doing this in other farms in South America when we have really high success. But here it was a challenge from the last year when we came here and we learned about the TMR and we start our trials with that. This is the result 1 year to have this. But yeah, it's the piece of this, is the pace of the science, the pace. Let's back to our in vitro study. Then we took TMR from New York dairy farms, some samples last year. We have treatments, control, and forced feed. That is the name of the consortium that we have, the microencapsulated consortium. We did replicas per treatment and different times of incubation. Then we take a sample during 16 days. Focus on dry matter degradability, efficiency as an efficiency indicator, but also microbiota and short-chain fatty acid production, or acid lactic production. Then what are the results? We were able to improve the degradability up to 1.5%. As I mentioned at the beginning, improve 1% in the degradability is a huge impact in the top dairy production. So that's what we get is important, because this relative improvement of 1.45 compared with the control group allowed us to infer a production up to 0.5 kilograms per cow per day. This is the graphs of the in vitro result that we have in degradability every day, and summarized in the box plot graphic. But then what happened with biological data? It's so difficult to get biological data if you want to try different microorganisms of different treatments. So we have a software that we have been training to improve and to produce simulation in silico in the computer that allowed, with a small biological data, infer what can happen in bigger amounts of data. And when we have differences as 1% or 1.45%, that is a small differences, we need to have a huge amount of data to make that these differences has a statistical differences. So we simulate in silico data based on the distribution that we have. Also, this simulation allowed us to confirm that these differences between treatments are statistically significant if we improve or increase the amount of bioreactors or of cow that we are under treatment. Then we can also simulate what can happen with control and with adding probiotics. And we have this rainbow of what can happen. But the important thing is we can move in those smooth or gray zones when we infer what can happen. But the important also is after the time, if we improve the retention time in the rumen, so the digestibility is also to increase. But if we have short time periods, like here with the TMR, so the digestibility is going to be less time to happen, so we will have less efficiency. And that's the key point. How we improve the TMRs, but maintaining a good time retention and using the proper microencapsulated additives that help us to have this difference and keep improving or boosting the productivity. At the end, what does it mean? Improve the degradability in 1.21 points is about 1.45%, allowed to invert about 0.3 kilogram milk per day per cow. If we project this per year, can be 110 kilograms per cow per year. A herd of 100 cows can be 10,000 kilograms milk per year, but here we know that some farms can be more than 2,000 cows or more. So the impact at this scale is huge. Just a graphic to show how this can be done. Final conclusion, Forsell improves ruminal fermentation consistency and degradability in TMR diets. Even small improvements translate into meaningful gains for high-producing dairy herds. Next step of this validation, we are discussing with some farmers to do pilot trials in commercial herds. So we are happy if someone would like to be part of this next step in our conquer of the dairy market in US. We will be happy to provide probiotics, the support and everything, and how to make the trials in herds. Also, yeah, basically we need to move into the in vivo trials and confirm that our simulation and our in vitro trials are good. So we are looking for this kind of partners here in New York and upstate of New York and here in Wisconsin. So happy to talk with you after this. That's what I want to present today, what we are doing here in US. And happy and glad to hear your comments and have a discussion. Thank you so much.
Hi, I actually have two questions. First, for your simulated digestive systems, are you mimicking the rumen or like the smaller intestine, hindgut?
Yeah, both parts even, yeah. The normal simulator just mimic the rumen, and they can be inoculate, that is with liquid, ruminal liquid. So that's one part. But then you can simulate the small intestine and connect it. So we have both parts. Ruminal part and see what happened with the community there and the production of short-chain fatty acid and everything. And then move to the small intestine part. So we can mimic both parts.
Okay, and then you said that you did see increases in different enzymes like amylases, cellulases, whatever. And then I think you touched on it, but maybe I missed it. Did you also see significant changes with like short chain fatty acids, pH changes, like you're actually seeing an effect from adding this probiotic?
Yes, yes. We have differences in the production and even in the ratio of propionic and butyric acid, and we compare what happened. Even in that slide, I think can be. Yeah, in this, when we have these pathways, in the pathways is also the production of short-chain fatty acids, so we can compare what happened with in vitro and in vivo. Do you have one question over there? Thank you.
I know you're in trial stage yet, but will there be a kind of an estimated cost of what would?
Yeah, yeah. We have a return of investment than 6 times the cost of the probiotic with the inference of improve in milk. So it's 6 times what you are investing. Okay, thank you so much for your time. Remember